Alright, this is part 2 of the PN junction. Welcome back. Alright, something I kind of forgot to mention. Sure, things will move if in a general drift if you have the overall battery voltage pushing and pulling in a certain direction, but even though you didn't have any battery hooked up, these conductive particles will be randomly just hopping around as, due to thermal vibration, kind of like the concept of Brownian motion. If you put a dust particle in water under a microscope, you can see it just kind of kicking around as random molecules are bouncing around due to temperature. These random molecules are bouncing around, and so they will get a chance to drift together, and these moving plus holes can move into this region, and these moving minus holes can move in this region, and they'll when they get close enough, a minus hole will be attracted to a minus electron will be attracted to the positive hole. Again, the positive hole is a missing spot in the lattice of the silicon, and the electron is like an extra freeloader electron kind of stopping by each silicon that they kind of put up with it for a while, but it's only weakly attracted to the silicon. And then these spaced out stationary plus charge are the creators of the original, once the initial virgin hop, when the electron left its home and drifted off into the lattice, it now has like a 1 in a million chance to accidentally get close enough to bump and land back on the stationary charge, so it can cancel it. But it can then, very soon be kicked loose, and it's not really held down by that phosphorus, because the lattice forces upon the phosphorus no chance to make 5 bonds, just 4 bonds with neighboring silicons. So it's always not really good, even though the negative electron returns home to a phosphorus, it'll temporarily cancel the minus charge, but it'll be off on its way to another journey to Central America, and because it's like a college student on a youth hostel urge, it's floating around. Alright, look at this. Let's look at the battleground where anytime a plus charge gets near a minus charge, they just sort of disappear into each other, and there's no longer a conductive moving thingamajig. So what you build up is, well, if you take away the minuses, you build up some plus stationary charge on the front lines of this battlefield, and in the P-type material you build up a front line of stationary minus charges. So at some point, since the minus charges are nearer and the plus charges are farther away for a little fellow plus charge here, how would it respond if it was kicked up in the air, actually if a neighboring electron was kicked loose and landed in there and made the electron move away? So is the electron going to move away? That's weird. It would be. So these minus charges, stationary, would tend to draw the plus charges closer. So I guess they'd be right, it would kind of put those plus charges right there at the front lines of the battlefield. I'll put that in a circle because this will hopped its way over. However, it now faces a line of plus charges, and we all know that plus repels plus, like charges repel. So when an electron here was knocked up in the air to be loose, instead of going away from the plus charges, it would be drawn towards the plus charges. So what we can see happening is then an electron waiting to be kicked loose in the bonding, the 4 bonds of the silicon, gets kicked loose and then can land here and fill the missing electron in that bond, and then the plus charge appears to move, but it's going to move because the electron is then attracted to the distant, it's a little bit distant, plus charge of the N-type material. Well, it makes the P-type material, P-type hopping thing move away. So another way to think about it more easily, but maybe not as exactly, the plus charge, you could say, is repelled by those plus charges and it hops away, making like a barrier for this to proceed anymore. It can't go on that way anymore. In reality, it's the electrons being attracted to the plus charge, leaving behind the plus hole more to the left, and then the electron moves more to the right. The end result is the moving charge carrier is being repelled. And now let's go over to the electron hole. Electrons that are just kind of loose, kind of easily hop from one atom to the next if they were given a little kick from the thermal stuff. So what is it going to feel? Well, it's going to hop right up to the front line since it's attracted to the stationary plus charges. So hop, 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 hop. And there's your moving minus charge. It moves, so I got to erase where it used to be. But now it experiences a comfort zone being into the stationary plus charges, and a danger zone, well, it's being repelled by these stationary minus charges. Minus obviously is known to repel minus. So in the region where P and N meet, the carriers are gobble themselves up, leaving a region void of current carriers. Now if I want to try to do something about that, let me, how would this go? Let's reverse our battery just for the sake of a hypothesis. We're going to now put minus and plus. That's the direction of our battery in this overall material. So minus on this side and plus on this side. Alright, now if I did that, well, plus means it draws electrons to it. So these electrons would move into the metal, and making these kind of go that way, well, that's going to make the situation worse. If there were no carriers here and I try to go that way, yeah, I can see the movement of the electrons, but at some point they'll stop moving because of these stationary plus charges. There's just too much plus charges and it'll counteract the battery, and they just won't, okay, yeah, the battery pulls that way, but then these plus charges pull it back, and it just reaches like a stop. Nothing more moves. Now let's try to understand that the whole side, the P-type material, it again is interfaced with a metal wire, is bonded by high temperature. I learned how to spell metal. So yeah, we put a minus battery voltage, which means we push on electrons. So if I did have a carrier and I'm pushing on electrons, when it gets loose, it'll hop in the air, pushed, and it will land in that hole, that missing spot in the lattice, and now the plus would move closer to the minus, and the electron would move away from the minus because it's repelled by the minus. So the end result is the plus moving holes would be seen to be drawn to the minus charge. In reality, it's only electrons moving, so it's basically just the electrons hopping into the holes, and then the hole appears more closer to the metal. But in the end, we have the same problem, a whole bunch of stationary minus charges, and if we start sucking out too many of the plus charges, which can, appear to move, you've then left this negative charge, which would mean it would attract the state, it would attract back in the moving plus charges, or in other words, another way to look at it is the minus charges would then repel the electrons to hop in that direction, bringing the plus more into the zone. So again, current flow stops because the battery's push of negative is met with the negative charges. So if you try to, which would then grow as you take out more of the plus charges, the negative charges would grow, so it would stop the minus charges from being pushed in. It's a bit more abstract on the P side, P-type material side. But there you go. That is what's happening when you put a negative charge on the P side and a positive charge on the N side. It makes the middle region devoid of moving carriers, and the current stops. So this is what's called a semiconductor diode. The electrons cannot travel in that direction. I guess here's the secret. If you keep on increasing your voltage until these carriers finally reach the point of the metal, something happens and the diode no longer works, and then the electrons just make their way across. But I'm gonna have to tag team this to you. This old brain is this is what I can remember of these ideas. So this direction, if you don't overstress your diode, the current will flow for a tiny bit, but then stops. I mean a super tiny bit, and then stops. Now let's do the high thought experiment. Einstein used to like to do thought experiments and anonymously publish them in the local newspaper of his town. Fun little thought experiments for the kiddies and the adults. He did not want to be known to be the famous guy writing them. So he made up an avatar. All right, let's. I don't want to erase metal. Let's take our battery now and do the minus push electrons in that direction, plus push on this side. So now we have plus there, so that means the electrons would want to move that way, and minus here, electrons want to move that way. Let's see, that's going to obviously push the negative carriers. They'll hop from the metal in here, move these along, so now we'll have more negative electrons coming together, and then the negative electrons as part of the lattice would, as they jostle up and become loose, would then be attracted to the nearby absence in the lattice, and they'd hop in, which makes the missing part now move, which of course makes it look like the plus carriers are then coming to that direction. And indeed, applying the voltage in that way would bring the plus closer and closer to the minus. And of course, we all know what happens when the plus hole gets pushed. It finds itself right next to the very loose electron. Flip, hop in, and now this is no longer a loose electron. It's found a home in the lattice. And for our observation of moving carriers, it's no longer moving carriers. They've combined. So putting the electricity voltage in that direction freely lets the plus charges push towards the center, freely lets the minus charges toward the center. They combine, current flows happily, and there's your diode functioning. I didn't actually think I'd get this far. Diode is functioning. It flows current in one direction and not the other. Alright, that's part 2, a little bit shorter than part 1. I'll have to get into transistors later. I have to try to bring that out from memory, but thank you for listening, and enjoy.